All right, in this video, we're going to be talking about prime numbers, prime factorization, and then the title of the video, or I might title it something else, greatest common factor and greatest common factor of monomials. So to start off, we're going to talk about prime numbers. So prime numbers, by definition, are only divisible by 1 and itself. So if we look at the list of prime numbers here, we have 3, we have 7, we have 11, we have 13, we have 17. Okay, so notice how 3 is only divisible by 1 and 3. 1 times 3 are the only two numbers that give me 3. As with 7, only 1 times 7 gives me 7. So 1 in itself. Same thing with 11, 13, 17, and so on. So ones that are not prime numbers, so we have examples here. I have 4, 6, 8, 9, 10. Well, 4 is divisible by 2, and 2 is not 1 or 4. 6 is divisible by 2 and 3. 8 is divisible by 4 and 2, 9 by 3, 10 by 2 and 5. So knowing the difference between prime numbers and not prime numbers. So basically they can't be divided by anything other than 1 in itself. Now prime factorization, every number can be factored into a product of prime numbers. So each number has a unique prime factorization. So no two numbers will have the same prime factorization. So basically all it is it's a bunch of prime numbers that are being multiplied together to get you a, well, bigger number. And we're going to use factor trees to do this. And you'll kind of see why they are named factor trees. So what you're going to do is, and if we look at the first one here, we have 39. You're going to think of two numbers that multiply together to give me 39. Okay, so you might say 3 and 13. Okay, so we'll go ahead and do that. So split it up like this. We have 3, and then we have 13. Now, these right here, 3 and 13, if you can break those down even more, go ahead and do it. But notice how 3 and 13 are both prime. So the prime factorization of 39 is just 3 times 13. So we just multiply those numbers together. Let's take a look at 100. So there are many ways you can break up 100. You can go 250 or 25 and 4 or 5 and 20. Let's do that one, 5 and 20. Okay, so we have 5 and 20. So notice how 5 is prime, so I can't break that one up anymore. I'm going to circle it for now. And 20 is not prime. I can actually break that down even more. So with that, make our two little lines. And what are two numbers that multiply to give me 20? Well, you can say 2 and 10 or 4 and 5. Let's go with 4 and 5. Okay, so now I got 4 and 5. 5 is prime, so let's circle it. 4 is not because I can multiply 2 times 2 to get that. Okay, so is 2 prime? Technically 2 is prime, so you might think that all even numbers are, and if it's not prime, it's composite, but 2 is actually still prime, so the only even number that is prime. So I have 2 times 2 times 5 times 5. So I'm going to write it like this for now, but what I actually want you guys to do is 2 times 2, that's just saying, well, 2 to the second power, an easier way to write it, and 5 to the second power. So those exponents tell you how many of each number are being multiplied. All right, 64, let's break that up. I can use 2 and 32. Okay, 2 is prime, so I'm going to circle it. I can break up 32 even more, so 2 and 16. 2 is prime. 16 I can break down even more, so I have 2 and 8. Circle that. 8, divide by 2 again. And 4 I can divide by 2 as well. So I have 1, 2, 3, 4, 5, 6 2's. So 2 to the 6th power is my prime factorization. Okay, so just a couple more of these. 32, I can break that up into 8 and 4. There's one example. I can actually split up 8 into 4 and 2. 2 is prime. I can split up this 4 into 2 times 2, so the 2's are both prime. And 4, again, I can split up into 2 times 2. So how many total 2's do we have? We have 5. So 2 to the 5th is the prime factorization. So you could do these problems differently. You should get the same answer, though. So at the beginning, you could have said instead of 8 and 4 here, you could have said 2 and 16, however you want to think about it. 120. So how about we do 6 and 20? 6 times 20 will give me 120. I can break up 6 into 3 and 2, which are both prime. I can break up 20 into 5 and 4. So 5 is prime. 4 is not, so I can break 4 up even more. So 2 times 2, and those are both prime. So how many 2's do I have? I have 1, 2, 3, so 2 to the third power, times, okay, I'm done with the 2's, 3, okay, done with the 3, and then times 5. And that is my prime factorization. And you might notice how I go from the lowest prime number to the highest prime number. It's okay if you don't do that, but kind of organizes your mind a little bit about what prime numbers are inside that prime factorization. The next topic, we're going to get into greatest common factor. So a greatest common factor is a number that divides, and if you're looking at 2 or 3 numbers, divides all those numbers, whether it be 2, 3, 4, or whatever, and it is the biggest one. So if you look at 15 and 40, now you can do this a couple different ways. Some of you might be able to just do it in your head and say, well, let's just see what numbers divide both of those, and then what is the biggest one. Now, a pretty straightforward way of doing this is just look at the numbers separately, so 15 and 40, and see what numbers divide 15 and 40. And then we'll look to see which ones they have in common. So if we look at 15, 1, of course, divides everything. I have 3. I also have 5. And I also have 15. So notice how you're always going to have a number with another number. So notice I have kind of a rainbow effect. 3 times 5 multiplies to give me 15. 1 times 15 gives me 15. Unless you have a number with itself. Let's take a look at 40. Well, 1 divides 40. 2 divides 40. 3 doesn't. 4 divides 40. 5 divides 40 because anything that ends in 0 or 5. 6 does not. 7 does not. 8 does. 8 with the 5 gives me 40. Okay, 9, 10. 10 with the 4 gives me that. And you can get the idea. So we have 2 and 20. 2 times 20 gives me 40. And of course, itself. Now, looking at those two lists, we have to look at which ones do they have in common? Well, they have the 1 in common for sure. 3 isn't in with the 40th list. 4 isn't with the 15. The 5s are in common. And there's no 15 in the 40. So actually the biggest number that divides both of them is 5. So the greatest common factor of this one will be 5. Let's take a look at 17 and 16. Numbers that divide 17, well, I got 1 and 17, because 17 technically is prime. So only 1 and 17 will divide it. If I look at 16, I got 1, 2, 4. 4 with itself will give me 16. 2 times 8 will give me 16, and then 1 and 16 will also give me 16. So you might notice on this one, well, the only ones that are in common are 1. So the greatest common factor of this one is just 1. The name of the game here is you're finding a number that divides both of the numbers that you can divide out of them, and we want the biggest one. A little trick, if one of them is prime, it's always going to be 1, because that's the biggest number that can divide it. Unless that number itself was a factor of the number. So if we had like 17 and 34, 17 would have 1, 17. 34 would be like 1, 2, 17, and 34. So in that case, 17 would be. So I guess all the time it's not going to be 1, but sometimes it will. But just make sure to think about it. 50 and 75. So looking at 50, we got 1. We have 2. We have 5. Okay, 6, 7, 8, 9, not until 10. Okay, 5 times 10. 2 times 25. And then we have 50 at the end. And if we look at 75, I have 1. I have 3. I have 5. I have 25. Okay. So 25 and 3. Actually, there is one in between 5 and 25. Should be 15. So 5 times 15. 3 times 25. And then 1 and 75. So which one is the biggest number in both of them? There are 1s in common. There are 5s in common. There are 25s in common. So actually, 25 is the biggest one, and 25 is my greatest common factor for that one. All right, let's try out a few more. So 18 and 36. So for 18, I got 1, I have 2, I have 3, I have 6. 6 times 3 gives me 18. 2 times 9. You might know it's kind of a rainbow pattern that you get with these. And then 1 and 18. Kind of how I look at these is I just basically think of two numbers that multiply to give me the number. So for 36, you got 1, and on the end, I'm going to put 36. Okay. 2, since it's even. 2 times what number? Well, 2 times 18. Okay. 3 will work. 3 times 12. 4 will work. 4 times 9. And then I have 1 left because 6 times 6 gives me 36. So 6 goes in there. So that with itself, go like that, boom, boom. And we notice that, oh, 18 is the biggest one out of both of those. So 18 is the greatest common factor. It'll never be bigger than your lowest number, because a number bigger than your lowest can't technically divide it. 100 and 120. So for 100, we got 1, we got 2, we got 4, we have 5, we have 10, a lot of them here. So 10 times 10 gives me 100. 5 times 20 will give me 100. 4 times 25. 2 times 50. And 1 times 100. I don't think I'm missing any there. And 120, I have 1, 2, 4 will divide it. 5. 10 will divide it. So 10 times 12. 5 times should be a 24. 4 times 30 will give me 120. 2 times 60 and 1 times 120. Okay, so the biggest one, and I actually think I'm missing one here. I should have a 20. Yeah, 20 and 6 should be in there too. So 6 and 20. Because actually, if you look at these, the biggest one in each is 20. So 20 is the greatest common factor for that one. All right, so the next topic I'm going to talk about is the greatest common factor of monomials. So monomials are a product of variables or certain numbers together, as we have 12y to the third and 15y squared. And what we do to find the greatest common factor of these guys is we first, step one, need to find the greatest common factor of the coefficients. And remember, the coefficients are the numbers at the head of the monomial. Step two, if the variables have, or if the monomials have variables in common, then we're going to use the lower power. So let's use this one for an example. The greatest common factor of the coefficients, 12 and 15, that's going to be 3. Okay, so 3 is the biggest number that divides 12 and 15. Step 2, if there are variables in common, so what that means, are there x's, are there y's, are there z's, are there a's in both? In this case, yes, there are y's in both. If that's true, use the lower power. So which one has the lower power, the cubed or the squared? Well, y to the second. So always just use the lower one, because you can at least take out that many in both. You can divide out that many. Let's go through a few more. So we have 3p to the fourth and 4p. So out of 3 and 4, what is the biggest number that can divide both of those? Well, it's just 1. Then I have p to the fourth and p, so there are p's in common. So I circle them both. Imagine that's a p to the 1. Okay, so which is the lower power? Well, the p to the 1. So I'm just going to put a p. You don't need that p to the 1. You don't really even need that 1 there at all either. So just a p. That's all you can divide out of that. 21m to the third and 28m. So out of the coefficients, I can divide 7 out of both of them. And then I have a variable in common. I have m to the third and m. So use the lower power. So that'll be the m. So 7m. 13x and 26. What can I divide out of 13 and 26? 13 can divide both of those. Now this one, I actually don't have variables in common. One has an x, one does not. So I can't include a variable here because it's kind of like you're saying they at least have that many x's. So if I would have put an x here, that's saying that, well, off of this one and this one has to at least have an x, and so does this one, but that one does not. So that's what we leave off there. Going back to the previous examples, it's saying 7's the biggest number that divides it, and they at least have 1m. Okay, 28m has at least 1m. And up here, only one can divide the numbers in front, and p is the lowest, how many variables we have in each binomial. Okay, so moving on, just a few more problems. I have 2 and 4, so 2 is the biggest number that divides both of them. And these ones, they have 2 variables. So this one has x's in common, x to the second, x to the third, the lower power, so we use x to the second. They have y's in common, so y and y to the second use the lower power. So 2x squared y. Out of 30 and 36, we can divide both of those. That should be a 6. And then I have s's in common, so use the lower one, s to the third. I have t's in common, so t to the fourth is the lower one. Continuing on, and these ones have a negative. Now, the negative is just kind of throwing you off. You don't really even need to worry about the negative. So 8 and 12, ignore the negative. It's just trying to throw you off. 4, because 4 can still divide negative 12. Okay, so I have x squared and x to the third. X to the second is the lower one, and then the y's, just a single y is the lower one. So 16 and negative 8. Well, 8 divides 16 and 8, so let's write down an 8. I have x to the third and x squared. The lower one is the squared, so we'll write that down. I have y to the fourth and nothing. So I cannot include a y. They have to be common in both. That's why they call it the greatest common factor, because they have that in common. So to finish off the video, we're going to be discussing a word problem. So Kirsten is decorating her bedroom wall with photographs. So she has 36 photographs of family. So I'm going to designate that blue. So blue are the family. And 28 photographs of friends. So those are the friends. So she wants to arrange the photographs in rows so that each row has the same number of photographs. Okay, so whether it be 6666 or 7777 or all that stuff. So each row has to have the same number of photographs. And the photographs of family and the photographs of friends do not appear in the same row. So we got to keep them separate. So we got to keep, let's do the family up here, and then we got to do the friends, however many number of rows it may be. So question A asks, how many rows will there be if Kirsten puts the greatest possible number of photographs in each row? But actually, if I look at B first, how many photographs will there be in each row? That might be actually a better thing to answer first before we go on to A. So how many photographs will be in each row? Remember, every row has to have the same number of photographs. So what we're going to do is find a number that divides 36 and 28, or the greatest common factor, and the greatest number of photographs in each row. So 36 and 28, the greatest common factor of that is 4. Okay, seems kind of small, but that is the biggest number that divides both of them. So there's going to be 4 in each row. So it's going to look something like this. So with the family, I got 1, 2, 3, 4. Another row, 1, 2, 3, 4, and so on and so forth. And that continues. And then the photographs of friends, 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth. So question A asks, how many rows will there be if she puts the greatest number in each row? So I had to find the total number of rows here. So if you look at the family, there's 36 total photographs. So if we put 4 in each row, well, 36 divided by 4 will give me 9. Okay, so there's going to be 9 rows of the family. And then how many rows of the friends are there going to be? Well, there's 28 of those. So 28 divided by 4 will give me 7. Okay, so 9 of the family, 7 of the friends, add those up. That gives me a total of 16 rows. So greatest common factors are good if you're lining things up in a nice rectangular fashion and stuff like that.